And I'm very privileged because I get to thank both the co-organizers for giving me the opportunity to co-organize this conference and the scientific committee for suggesting that I give a talk in my own conference, which is a bit uncomfortable, but still, I'm very happy. So I want to talk to you about a very recent joint work with Andrés Navas, and you're going to see that in my talk there are going to be many tools that actually Andrés already mentioned, but they are going to be used in a different context, which is the context of distortion elements in groups of interval diffeomorphisms, which is a subject I'm not a specialist of. There are many specialists in the room, so if you want to ask some technical questions, I will tell you their name. Well, there is Emmanuel Militon, there is Catherine, there is Andrés, there is Sam Yun Kim, well, many people who know much more than me, and you will see that very soon I will talk about something which I know much better, which are conjugacy classes of diffeomorphisms. But still, I'm going to start with this very, very general notion of distortion elements in groups. So this can be defined. First, I need a definition in finitely generated groups. So let gamma be a finitely generated group, and S is a finite generating set. And we are going to say that G in this group is distorted if, when you look at the word length of G to the n, so this grows sublinearly in n. So if you divide by n, this has a limit, and the element is said to be distorted if this limit is 0. And this actually doesn't depend on the generating set. So it's really a notion about being distorted in the finitely generated group. And if you deal with groups which are not finitely generated, you can define for any group G, you say that an element is a distortion element if it is distorted in some finitely generated subgroup of your big group G. And I'm going to give you two very simple examples. The first one, I'm not going to use it in this talk because this will never happen. These are torsion elements of a group. So if G to the K is equal to the identity, then in the subgroup generated by G itself, the word length of G to the n is bounded. So if you divide by n and you let n go to the infinity, this goes to 0. But the second example, which will, on the contrary, be very useful in my talk, is the situation where there exists some element phi in the group and some integer k, such that my element G is conjugated to its kth power. Then you can see that K was a bad notation, but anyway, phi to the n G phi n inverse is equal to G to the K to the n. And thus, if you look at the word length for the generating set phi G phi inverse of G to the K to the n, this is less than 2n plus 1. And if now I divide by the corresponding power, K to the n, this goes to 0 when n goes to infinity. And actually, I said that this always has a limit because the word length is subadditive. So if this goes to 0, actually you can show that this limit is 0, and so the element is a distortion element. Okay? And very quickly, why can this be a useful notion? If you have a big group which has, let's say, no non-trivial distortion elements, and you have another group with non-trivial distortion element, then the second one cannot embed in the bigger group. And in particular, if what you're looking at are automorphism groups of some spaces, like a manifold with some structure, and this big group has no distortion elements, this can provide some obstructions for some other groups to act faithfully on it. So that's very useful. I'm actually going to look at groups of diffeomorphisms of a manifold, a very complicated manifold, as Christian mentioned to me. And he has some groundbreaking new theorems about the algebraic structure of this of the groups of the interval preserving the volume. And anyway, sorry. So I'm going to look at this group in basically 3 regularities, 0, 1, and 2, and there will already be something to say. The first thing to say is that these 3 groups do have some non-trivial distortion elements. And this is because if I look not at the interval but at R, and I look at the translation by 1, it's conjugated to its square by the homothétie of ratio 2. And this action can be compactified to the closed interval in regularity as high as you like. So you can find 2 diffeomorphisms, infinity diffeomorphisms of the closed interval, with one which plays the role of the unit translation and which is conjugated to its square by some other smooth diffeomorphism. So basically I'm saying that this group contains obviously non-trivial phi and g, such that phi g phi inverse is equal to, and in my talk I'm going to always say g to g squared, but you can put any power you like, it doesn't change anything for what I will say, it's just to reduce the amount of notations. So you do have distortion elements, but my point here is to try to characterize them all, to understand all the diffeomorphisms in a given regularity which are distortion elements. And let me start, that's a spoiler, I will not answer the question, but well, that's the goal. If I start with homeos, simple remark is that in this group, everyone is a distortion element because everyone is conjugated to its square. Just because if you have, say, start with a homeo without interior fixed point, it's conjugated topologically to any homeo which has the same dynamical behavior, namely without interior fixed points and pushing everything in the same direction as the original one. Because if you remove the endpoints, you just have something which acts like a translation. And topologically, you can compactify, and they are pairwise conjugated. And obviously, if you have an F without interior fixed points, its square is going to look something similar without interior fixed point and pushing everything in the same direction. And if you have fixed points, you can just conjugate F to its square on every component of the complement of the set of fixed points, and you glue all the conjugacies together, and it gives you a conjugacy of the whole segment. So there is nothing interesting to say about distortion elements in this group because everyone is a distortion element. Obviously, what I said doesn't work in higher regularity, and we're going to see how much it doesn't work. So just to say, there are other manifolds for which one can say that every homeo is a distortion element. This is not true in general for any manifold. This is a very specific situation. Okay. So I'm mostly going to be interested in these two regularities. And if I want to, I'm going to give you in just a minute examples of diffeomorphisms which cannot be distortion elements. And for that, I need a criterion. I need an obstruction to being distorted. So that's going to be my first part. To present you some natural obstructions to distortion. And the question will be whether they are the only obstructions. And here you're going to see that there are lots of things in common with Andres' talk. So in a general G, if you have a map that goes from your group to the positive numbers such that L of GF is less than L of G plus L of F, then again L of F to the n defines a subadditive sequence. So if you divide by n, you get a well-defined real limit. And I'm going to define it as L infinity of F. And if you have if this quantity is positive, then you cannot find a finite family generating F and such that the powers of F can be written as words in this finite family with length small compared to n, because otherwise this quantity would be small compared to n, and this would be 0. So this implies that F is not a distortion element. And we're going to see two examples of such functions for our two spaces. In this one, I'm going to look at the map that to some C1 diffeomorphisms associates the uniform norm of the logarithm of its derivative. And because of the chain rule, it is true that you have this subadditive behavior. And thus, you can define this quantity for every C1 diffeomorphism of the interval. And what is this quantity? Concretely, this is the maximal Lyapunov exponent. So this is the maximum for x in the fixed points of f of the logarithm of the derivative of f at this point. You can show that. Okay. So basically, this quantity is 0 if and only if f has only parabolic fixed points. Okay? And thus, f is C1 distorted, is a distortion element of the group of C1 diffeomorphism. Well, if it is C1 distorted, then it must have only parabolic fixed points. And my first question is whether the converse is true. And this is not known. But before I give you some more comments about this question, let me look at the case for diff2. Oh, okay. So this already gives you plenty of examples of C1 diffeomorphisms, which are C0 distorted, because everyone is C0 distorted, but not C1 distorted, because if you have some hyperbolic fixed points, then you cannot be distorted. And let us see that there is also a difference between diff1 and diff2. I mean by that there are some further obstructions to distortion in diff2, well, which are not defined in diff1, but I'm going to make my statement more precise in a minute. So let me look at the map, and you're going to recognize something here, which is the L1 norm of d log df. And as we saw in Andres' talk, this affine derivative also has a chain rule, which has the consequence that if you compose two diffeomorphisms, the derivative of the log of the derivative of fg in L1 norm is smaller than the analog for f plus the analog for g. So this gives me a second quantity. So this is a real number, and this is what Andres named the asymptotic variation of f. And we have seen, and I'm not going to prove it, that this quantity is 0 if and only if f embeds in a C1 flow. And this is a joint work with Andres. With only parabolic fixed points. So in particular, if you manage to construct a C2 diffeomorphism of the interval, which has only parabolic fixed points, no, I said it wrong. Okay. In particular, you can find some diffeomorphisms, C2 diffeomorphisms, which have only parabolic fixed points and which are C2 distorted. And Andres used this to actually prove that there are some C2 diffeomorphisms which are non-distorted in this group, but which are distorted in this group, but for some non-obvious reason. Like, I don't remember the number of generators you need to write your diffeomorphism, but okay, you don't either. Okay, just to say, they are not C1 distorted because they are conjugated to a power of themselves, for more complicated reason than that. Okay, and again, if f is C2, so f is in this group, C2 distorted, then its asymptotic variation must vanish, and the question is whether the converse is true. Let me just make a short pause to tell you that these candidates, so these are the candidates for C1 distortion, and these are the candidates for C2 distortion. And actually, they are distorted for some different notion of distortion, which is related to putting a metric on your group and to, well, I'm not going to enter into the detail. And you can rephrase my questions as, do these two notions of distortion, the one I explained at the beginning of the talk, and the other notion of distortion, which means this and this in the C1 and C2 settings respectively, do they coincide? Okay, so as I said, I don't know the answer to these questions. What I want to say today is that you can be a little bit more, less ambitious and not try to prove that every C1 diffeomorphism with only parabolic fixed point is distorted, but that many of them indeed are. And it, of course, depends on the sense that you give to the word many. And I'm going to state 3 theorems slash observations about this. So we saw at the beginning that being conjugated to a positive power of oneself is a sufficient condition for distortion. So the first observation is that, and this is all, I'm not going to repeat it, this is all joint work with Andres, I just erased it. In the space of C1 candidates, so let me recall, it means just C1 diffeos without hyperbolic fixed points. The C1 distorted ones, the ones that are C1 conjugated to, let's say, their square, is dense. Unfortunately, the second result I'm going to state tells us that this cannot be a strategy to prove what we would like to prove, because on the contrary, in the same space, those that are not C1 conjugated to any power, but let's say to their square, is generic. So if all diffeomorphisms with only parabolic fixed points are distorted, it will be for some other reason than this one. And just, I'm going to focus on these 2 statements, but just to tell you, there's an analog of the first one in the C2 case. So in the C2 candidates, so the ones which have vanishing asymptotic variation, the ones I'm going to use this notation for the conjugacy. The ones that are C2 conjugated to their square is dense also. But probably many are not, except that in this context, the C2 candidates do not form a closed subset of the space of C2 diffeomorphisms. So talking about generic is a bit more complicated. OK, so so actually, I'm going to focus on the first 2 theorems. I'm not going to exactly prove the second one. If I have time at the end, I would give you the ingredients for, we actually have 2 proofs, which are based on very different results. I'm going to prove a weaker version of theorem 2, because then the proofs of theorem 1, theorem 2, and theorem 3 follow the same pattern, except at the end where they diverge. And I'm going to say that in the same space, those that are not conjugated to their square is dense, which is much weaker, but I don't have time to explain everything. So, so these are the 2 statements I want to focus on. Theorem 1 and theorem 2 prime. OK. Any questions? Nope.
What are the ones? I mean, what is the statement of
of C1 candidates. So in the space of C1 diffeomorphisms without hyperbolic fixed points, the ones that are C1 conjugated to their square is dense.
To the square? Ah.
To the square or to any power. To all of their positive integer powers, if you like. So in order to understand which diffeomorphisms are C1 or C2 conjugated to their square, we need to understand conjugacy classes of diffeomorphisms. Conjugacy classes of C1 diffeomorphisms is a complicated thing. What is much less complicated is C1 conjugacy classes of C2 diffeomorphisms. Or C infinity, if you like. And I'm going to restrict to diffeomorphism without interior fixed points at the beginning, and then we will see what we'll do. Okay, so these are very well understood. Basically, if f and g, so f is C2, g is C2, they have no interior fixed points. Okay, and even I'm going to say, to fix the ideas, diffeomorphisms without interior fixed points and which are above the diagonal, which push everything to the right. So any two such C2 diffeomorphisms are C1 conjugated if and only if, first obvious necessary condition, they are locally near 0 and 1. And the second condition is they have the same matter invariant. So this was defined very quickly at the end of Andres' talk. I'm going to go. I'm going to redefine this. So what is the matter invariant, not to be confused with the matter morphism? The matter invariant of a C2 diffeomorphism of the interval without interior fixed points. One way of defining it is to say that if I start with such a C2 diffeomorphism, first you have some results of Sequeres and Coppel, which tell you that there exists a unique vector field, which I'm going to denote by xf, which is C1 on the semi-open interval and only continuous at 1, such that f is the time 1 map of this vector field. And you have the same thing on the right. So you have another vector field, which is this time C1 on the semi-open interval, but open at 0. So it's only continuous at 0, such that f is the time 1 map of this vector field. So these vector fields have the same time 1 map, but there is no reason why they should have the same time t map for every t. And there is no reason why they should coincide, and we will actually see how to prove that in general they do not coincide. We will use this for our proof. Tableau 2. So I'm going to draw basically the same picture as Andres drew this morning. So I have my interval diffeomorphism. I'm going to draw the orbit of a point. Well, this is not the orbit. The orbit is the projection of that. So that's my point P. Okay, this is the orbit of P under the diffeomorphism F. And I'm working on the closed interval, but on the interval open at 1, I have a vector field X. On the interval open at 0, I have a vector field Y. So on the interior of the interval, I have two vector fields. And so I can parameterize my interval in two different ways. By associated, so this is R, this is R. Here I map T to the flow, the position of P at time t if I follow the flow of X. Yes, note that both X and Y are positive inside the interval. So if I start at P and I follow the flow of my vector field X, I will go to 1 in the future and to 0 in the past. And I have another parametrization. So 0, yes, I have to change colors. Again, at time 0, I'm at point P. And what is the image of my orbit in these two parameterizations? Well, in this chart, F is just the translation by 1. This conjugates the action of F to the translation by 1. So here I have F. Here I have the translation by 1. And it's the same on this side. So these two diffeomorphisms from the line to the open interval conjugate my action to the unit translation. So if I look at the transition map between the two, from R to R, it conjugates the unit translation to itself. So it commutes with the unit translation, and this is this transition map that is called the matter invariant of F. And so it commutes mf of t plus 1 is mf of t plus 1. So actually, it descends to a diffeomorphism of the circle of the same regularity as F, which I assume to be C2. Actually, you saw that I chose a base point P for these parameterizations. I decided I send time 0 to P, and then I parameterize the interval by the orbit of P. I could have chosen another point. So this gives me actually a matter invariant associated to P. And as Andres said this morning, if you change the base point, basically you're not going to change the matter invariant. You're just going to pre-compose and post-compose it by a translation. So it's basically the same. But now I can let me see. Yes, another way of saying that, sorry, this might be useful for the what follows, is that when you look at your point P and you look where you get when you follow the flow of x during the time t, it's the same thing as starting at P and following the flow of y, but during time mf of t. So this is the reparameterization, the time reparameterization of the flows. And now I can make my statement here more precise. And yes, this is due to matter. So f and g are C1 conjugated if and only if they are near 0 and 1. Sorry, I forgot just one little thing, which will be useful for later in the talk. Now, what the matter invariant obviously measures is the lack of coincidence between the Sekeres flow on the right and the Sekeres flow on the left. And what I'm saying by that is that if x and y coincide, obviously this is going to be the identity, and conversely, if this is the identity, the vector fields coincide. So the matter invariant is equal to the identity if and only if f embeds in a C1 flow on the whole interval, because we already saw that it embeds on a C1 flow on the interval minus 1 point. That is always true. But for it to coincide with a C1 flow on the whole segment, it needs to have a trivial matter invariant. What is less obvious is what is the connection between this object and the conjugacy classes. So what I stated above, and I'm going to state more precisely, f and g are C1 conjugated if and only if they are near 0 and 1, and there exists 2 points, P and Q, such that the matter invariant of f with base point P is equal to the matter invariant of G with base point Q. And I'm going to make a very, I'm going to wave hands to give you the proof. First thing is that if you have a local conjugacy at 0 from F to G, C1 conjugacy, obviously, you can extend it to a C1 conjugacy on the interval minus 1. Just by writing the conjugacy relation, there is a unique way to extend your conjugacy to almost all the interval except 1. And same thing, if you have another conjugacy at 1, you can extend it to a conjugacy on the other semi-open interval. So I assume that this is true, and I want to prove that f and g are C1 conjugated on the whole segment. So now I just have one conjugacy on almost all the interval minus 1 and on almost all the interval minus 0. The first thing I claim is that composing phi 0 with some element of the C1 centralizer of F, and this is an element of the flow of X, the C1 centralizer on the left, you can assume that phi 0 sends P to Q. And similarly, composing phi 1 with some element of the C1 centralizer of F on the right, you can assume that your phi 1 sends P to Q. So you have two almost conjugacies. They both send P to Q. And now what I'm saying is that they are equal. And why are they equal? Because the transition map from the flow of X for, sorry, this is F. This is for F. The transition map from the flow of XF to the flow of YF is the same as the transition map from the flow of XG to the flow of YG. You have to write it down, but if they send, they both send P to Q, and the transition maps are the same for G and for F, these two conjugacies actually coincide on 0, 1, which means that you have a global C1 diffeomorphism. I just made this very quick sketch of proof to warn you about the fact that, unfortunately, this does not generalize to higher regularity. You could want to write that F and G are CR conjugated if they are CR conjugated near the boundary and they have the same matter invariant, which are CR diffeomorphisms. But this doesn't work, because here, to construct my conjugacy, I composed with maps from the C1 centralizer, and these maps usually are not more than C1. So this complete description of the C1 conjugacies of C2 diffeomorphism does not generalize to the description of CR conjugacy classes. So it's all another problem. But this was a bit aside of my topic. OK, so we can now, I finished what I had to say about the matter invariant, and we can now use it, to prove our two theorems. No, I didn't finish. I still have one more thing to say about the matter invariant. And since I won't have time to enter into much detail, I'm going to have to ask, or maybe it's not a good idea to erase the statements. I'm going to describe another way, but very similar actually, but to describe another way of seeing sorry, I don't remember if I do this now or a bit later. No, a bit later, sorry. So the relation with our theorems. Yes, I forgot a very important thing that I should have said. I told you I'm not going to focus on C1 conjugacy classes of C1 diffeomorphisms, but I want to prove that C1 diffeomorphisms conjugated to their square are dense in the set of C1 diffeomorphisms. So I should have told you the following affirmation. Actually, C infinity diffeomorphisms with a finite number of fixed points, all parabolic, are C1 dense in the set of candidates. In C1 diffeos without hyperbolic fixed points. So the idea is that if you start with any C1 diffeomorphism with only parabolic fixed points, you first approximate it by a smooth diffeomorphism with only parabolic fixed points and a finite number of them. Okay? And then I want to show that among these ones, those that are conjugated to their square are dense, and those that are not conjugated to their square are also dense. Okay. So let me give an interpretation of this in terms of the matter invariant. So what does it mean? For a diffeo without interior fixed point, C2 diffeo, I claim that it is C1 conjugated to its square, if and only if, of course, this is true near 0 and 1. Okay, this hasn't changed. And from what I've written before, the matter invariant of f must be equal to the matter invariant of f squared. But what is the matter invariant of f squared? If you have f squared, the flow C1 on the left that generates f squared is twice the vector field that generates f. And the same for the vector field on the left. So it's not difficult to prove that the matter invariant of f squared is the matter invariant of f conjugated. I don't know in which direction, by a homothétie of ratio 2. And remember that the matter invariant is invariant on the translation, and if it also commutes with the homothétie of ratio 2, it can only be the identity. So this is actually equivalent to they are conjugated near the boundary, and the matter invariant is trivial. Remember, matter invariant trivial means embed in a C1 flow. So what we need to prove is that I'm going to stick to the case of diffeomorphisms without interior fixed point. I'm going to cheat and say that this is enough. I want to prove that among C1 diffeomorphisms, C2 diffeomorphisms, sorry, which are parabolic at the boundary, which have no interior fixed points, the ones that embed in a C1 flow are dense, and the ones that don't embed in a C1 flow are dense also. One direction, one claim is easier than the other. Okay, but let me write down what I want to prove. The second one, Andres almost already told it in his talk. It's generic, not to embed in a C1 flow. But I'm going to explain why, because we are actually going to use it for the other claim. And this is where I need a slightly different way of seeing the matter invariant. Instead of looking at the whole segment, I'm just going to look at two consecutive points, well, 3, of an orbit of F. I can parameterize this fundamental interval of F by 0, 1 using the flow of X. So the left Sekeres vector field. And I can parameterize the next fundamental interval by 1, 2 using the flow of Y. What I claim is that so this conjugates F to a translation, this conjugates F to a translation, and the map from 0, 1 to 1, 2, which consists in sending this to the interval, applying F, and going back, is this map. I claim it. You can check it. This is basically what the matter invariant measures. It's very, it can be confusing at the beginning because it looks like, since the matter invariant is commutes with the unit translation, and I've defined it on the interval 0, 1, I've defined it everywhere, and it only depends on F on 2 fundamental intervals. But this is not at all true, because hidden here, you have these 2 vector fields. And the definition of these vector fields does not only depend on what happens here, but on all the restriction of F to half of the interval. So this really captures the whole matter invariant. And what I want to say is that if I start with some F, and I create an F tilde, which is equal to F, except on this fundamental interval. I claim that actually the Sekeres vector field of F is going to be equal to the one of F tilde all the way up to F of P. And the right Sekeres vector field of F is going to be equal to the right Sekeres vector field of F tilde here. So so what do I want to say with that? Yes, okay, yes. So for my new F tilde, this map is the same. It's the same because I haven't changed the vector field X until F of P. For my map F tilde, this map is also the same because I haven't changed the vector field on this side. What only changes is F here. So what changes, and the way the matter invariant changes, and this is going to be a claim, I'm not going to prove it, but if your F is equal to F tilde, sorry, is F composed with some compactly supported diffeomorphism supported in this fundamental interval, your new matter invariant is going to be the same as F composed on the other side with some circle diffeomorphism, which is obtained from G. So G, okay, G is a diffeo of P f of P this can be sent using the flow of x to 0, 1. So from this G, I can construct a diffeomorphism phi G of 0, 1, which is the identity on the boundary. And I glue the two boundary components, and this gives me a circle diffeomorphism. And I claim that this is what happens to the matter invariant when you change the diffeomorphism only on a fundamental interval. You compose the matter invariant with something which is basically this G, except that it has been rescaled to be transformed in a diffeomorphism of 0, 1 with the boundaries identified. So, well, I have said more than enough to prove that if your initial diffeomorphism did embed in a C1 flow, I change it on just one fundamental interval by some arbitrarily small, C infinity small perturbation, if you like. I create some matter invariant. So I break the fact that my diffeomorphism embeds in a C1 flow. And this shows the density, and this is actually stronger than what I claimed, the density of these diffeomorphisms which do not embed in a C1 flow. And I have 3 minutes to tell you the more difficult part, which is actually an adaptation of works by Christian Bonatti, Amy Wilkinson, Sylvain Crovisier, and Gioia Vago, which tells you that, on the contrary, and this is not at all obvious, if you start with a diffeomorphism that does have a matter invariant, you can kill it by a C1 small perturbation. But if your matter invariant is not C1 small, you cannot perform a C1 small perturbation on a fundamental interval and hope to kill it by composing it by its inverse. If it's not C1 small at the beginning, this is not going to be a C1 small perturbation. So what you have to do is first some fragmentation of your matter invariant into small C1 small circle diffeomorphisms. And then, in order to kill all these fragments of the matter invariant, you're going to perform perturbations on disjoint fundamental intervals of your f, a finite number of time. And doing this, you're actually going to kill the matter invariant. What is not obvious is that it is not because your matter invariant was decomposed into C1 small fragments than the corresponding compactly supported diffeomorphisms here are going to be C1 small. So you have to control that. And actually, so the slight adaptation that we had to make is that in the article by the person I just cited, they consider the opposite case where the fixed points are hyperbolic. And when they are hyperbolic, actually they are affine, I think, in the paper. So really, the fragments here and the perturbations you have to make are conjugated by a homothétie. So it's not, I mean, once you have the fragmentation of the matter invariant, it's not so difficult to get a control on the fragmentation on the perturbed diffeomorphism. When it's parabolic, there's a little control of distortion to do in addition to control that. And I think I'm just going to conclude by saying that this does not work by a C2 small perturbation, because even if you fragment your matter invariant in C2 small things, when you conjugate a C2 small diffeomorphism of the unit interval to a C2 diffeomorphism of a very small interval here, you make the second derivative explode. And so this doesn't work, and actually it cannot work, because we have seen that being embeddable in a C1 flow is equivalent to have vanishing asymptotic variation, and this cannot be killed by a C2 small perturbation. So I think I will stop here.